In this video, I'm going to review the application questions. Notice that in question 6, the very first part of this calls for drawing the Lewis structure. So I'm going to stop and draw all the Lewis structures. I encourage you to stop and do the same, and then we'll come back and see how we layer valence bond theory onto our images. Okay, so now I have all of the Lewis structures. Check. Determine the electron domain geometry around each central atom, the type of hybrid orbitals that will be used, sketch the molecule and show all the orbitals, label the bonds as sigma or pi, and draw in the lone pair electrons as appropriate. So I'm going to do each one in turn. So I'm going to start with this molecule, which has a carbon-carbon triple bond. In this case, we have each central atom has 2 electron domains around it, and so the electron domain geometry is going to be linear for each of the carbons. And that means that I've got bond angles of 180 degrees, so each carbon is going to use sp hybrid orbitals. So if I want to draw those hybrid orbitals, I'm going to draw hybrid orbitals in blue. sp orbitals come in a set of 2. They're 180 degrees apart from each other. So there's the sps on the first carbon. And then the second carbon will have a similar set of sp orbitals. The hydrogen is going to bring its 1s orbital to come in and overlap. And notice that I have just drawn a sigma bond, another sigma bond, and a third sigma bond. So in the original Lewis structure, there were a total of 3 bonds in the triple bond, 4, 5. So I've now drawn 3 of the 5 bonds. The other 2 bonds are going to be pi bonds. They are going to be formed using p orbitals, one that goes up and down in the plane of the paper, one that comes out of the plane of the paper. And so I got a pi bond here, and then a second pi bond that goes in front and behind. So I've got a pi bond down here, and I've got a pi bond up here in the front. This molecule doesn't have any lone pair electrons, so we've now drawn the bonding. We've accounted for all 5 bonds by overlapping the atomic orbitals of hydrogen, the 1s's, with hybrid orbitals on the carbon as well as p orbitals on the carbon. Let's move to ammonia. So nitrogen in ammonia has 4 regions of electron density, a lone pair, and 3 bonds. And that means that the bond angle here is going to be, well, so the electron geometry is going to be tetrahedral. And the bond angle is going to be approximately 109, which is going to mean that the nitrogen is going to use sp3 hybrid orbitals. If we want to draw the hybrid orbitals, there's going to be 4 of them. And anytime you have an sp3 set, there will be 4. 1, 2, 3, 4. They're going to point towards the bonds. The hydrogens are going to bring their atomic 1s's. 1, 2, 3. And so you can see I have now drawn 3 sigma. That doesn't look much like a sigma, but it is. 3 different sigma bonds to account for each of the single bonds in ammonia. And the 4th hybrid orbital up here is housing the lone pair. Remember that nitrogen had 5 valence electrons to begin with, and what it has done is it put 1 in each of these hybrids and 2 in the lone pair. Hydrogen brought 1 in each of its 1s's, and so that's how we're going to share that electron. Okay, let's go to cyanide, Cn-. So what we can see is that around each atom, the carbon has 2 domains, a triple bond and a lone pair. The nitrogen has a triple bond and a lone pair, so each one has 2 domains. When you have 2 domains, that's a linear geometry, and as was the case up here, it means that we've got 180 degree bond angles, and we're going to use sp hybrid orbitals. If we draw the sp hybrid orbitals on the carbon, one will go here, the other will point out away from the bond. The nitrogen will have an sp here and another sp here. And notice that we have just drawn a sigma bond because the sp of carbon is overlapping with the sp, one of the sps on nitrogen. So one of the sps on carbon overlaps with one of the sps on nitrogen. The other sps, this sp houses a lone pair, this sp houses a lone pair. But we can see from the Lewis structure that there needed to be 3 bonds between the carbon and the nitrogen. So the other 2 bonds are going to be pi bonds. They're going to be formed by overlap between the leftover p's. So we get 1 pi bond here, and then we get another pi bond between the p orbitals that are coming out of the plane of the paper. So 3 total bonds shared between the carbon and the nitrogen. Okay, let's go to this structure here. Notice that around the nitrogen there's 4 regions of electron density, and that is also the case around the carbon, 4 regions of electron density. That means that each of these central atoms, both the nitrogen and the carbon, will be tetrahedral, approximate bond angles of 109, which means we're going to use sp3 hybrid orbitals again. In a lot of ways, tetrahedral centers are easiest because they don't have any leftover p's. The only thing that can happen when you have an sp3 center is it can form single bonds or it can house lone pairs. So let's look at what those hybrid orbitals do. So there's a set of 4 hybrid orbitals on the nitrogen, and then there's a set of another 4 on the carbon. Notice that this hybrid orbital here is housing a lone pair, and the rest of the hybrid orbitals are going to overlap with hydrogen 1s orbitals to form 1, 2, 3, 4, 5 sigma bonds. Let's look at oxygen. So here oxygen has 3 regions around it, a double bond and 2 lone pairs. That means its electron domain geometry, or its electron geometry, will be trigonal planar. Trigonal planar geometries involve 120-degree angles apart from the 3 different domains, which means that we're going to use sp2 hybrid orbitals on the oxygen. And so if we were to draw that, sp2s come in a set of 3. One is going to be here, and then we're going to have a trigonal planar arrangement on the first oxygen, and then a similar one on the second oxygen. Notice that I have drawn a sigma bond there, so I've taken care of one of the 2 bonds on the oxygen, and I'm just going to I'm going to draw some arrows. So these lone pair that I drew before are going to go in there. This lone pair is going to go in there. That lone pair is going to go in that space, and that lone pair is going to go in that space. We still have another bond to draw, and that's because the oxygens each have a p orbital left. So there's a p orbital that's in the plane of the paper, and those p orbitals can overlap, and now we get a pi bond. So this is an example of how hybrid orbitals, the sp2s, are housing lone pairs and forming a sigma bond, and the leftover p is forming a pi bond. If we look at this molecule here, we can see the carbon as the central atom has 3 regions of electron density. The oxygen, let's also look at that. That also has 3 regions of electron density. So each of these central atoms, and we in the past we wouldn't have thought about the oxygen as a central atom, but we have to figure it out as a central atom because we've got to figure out what to do with those lone pairs. So this has 3 regions. So each one of those is going to be trigonal planar, and that's going to lead again to sp2 hybrid orbitals. When we get a set of sp2s, they always come in a set of 3. They're in a trigonal planar arrangement. So here's the ones on the carbon. Here are the ones on the oxygen. And notice again, I'm going to have to move my lone pairs into these empty hybrid orbitals, sp2s. I have managed to draw a sigma bond connecting the carbon and the oxygen, so that creates the overlap that allows for the sharing of a pair of electrons there. Hydrogen is going to bring in its 1s's, so we're going to form some sigma bonds over here with the hydrogens as well. And we've got one more bond to form because we need 2 bonds between the carbon and the oxygen. So when we form sp2 hybrid orbitals, there's a leftover p, and I'm going to draw it in the plane of the paper, and it's going to overlap side to side and give us the second bond, which is a pi bond. Okay, a couple more. Let's look at the nitrogen, in this case, 3 regions around the nitrogen, 3 regions also around the carbon. So it is again going to be trigonal planar electron geometries, and that's going to lead us to sp2 hybrid orbitals. If we draw the hybrid orbitals, again they're going to come in a trigonal planar arrangement. Here are 3 orbitals on the nitrogen. Oh, and I just realized I hadn't drawn the hydrogen out here. Let's do that. Let's fix that. So the hydrogen is sitting out here. So those are the sp2 hybrid orbitals on the nitrogen. And if we draw the ones on the carbon, they're going to look like this. So trigonal planar arrangement. So what you can see is I've already drawn one sigma bond between the carbon and the nitrogen. And now let's add the hydrogens in. So one over here, and one over here. So that's 3 more sigma bonds. And we've got one more bond to draw between the carbon and the nitrogen. Each of the carbon and the nitrogen still have a p orbital that hasn't been hybridized. Because we made sp2 hybrids, that means we didn't use all 3 of the p's. So each one has a p orbital. It's in the plane of the paper in the way I've drawn it. And when we overlap it in both at the top and the bottom, we get a pi bond. Now I'm going to show you one more example that's a little bit different than the others. Cl2. We could, and it would be perfectly fine if you did this, say here's chlorine, it's got 4 regions, that must mean it's tetrahedral, and we could draw this as an sp3 hybrid and this one as an sp3 hybrid and overlap an sp3 from this chlorine with an sp3 from this chlorine. However, it does cost the atom some energy to hybridize its orbitals. So one idea in valence bond theory is that you only hybridize if you really need to in order to put things in the right geometry and actually have overlap. So I've drawn over here the valence bond electron configuration for the Cl valence electrons. I didn't draw the 2p, the 3s, I only drew the 3p. But notice that we've got a p orbital here that has a single electron in it. And so each of the chlorines have a p orbital that's half filled. And remember that in valence bond theory, the way you form a bond is by overlapping one half-filled orbital with another half-filled orbital. So one of the ways to draw this chlorine molecule, is to just say, you know what, I've got a p orbital on the first chlorine and a p orbital on the second chlorine, and I can overlap those. They each have 1 electron in them, and I'm going to get a sigma bond out of it. Now, what this doesn't show is what happened to the rest of the electrons. In a lot of ways, I like a more complete approach that accounts for all of where the electrons are, but there are valence bond theory approaches, and if you read Tro would treat it like this, where you only overlap orbitals, and you overlap orbitals if you need to create a bond, and you only create hybrid orbitals if you absolutely need to. One thing I'd like to do before we leave this kind of complicated example, notice that in the cases that were linear, that had a triple bond in them, the basic picture looks pretty similar. SPs overlapped with p orbitals that form pi bonds. In the case of situations where you had a tetrahedral center, sp3s, here's a single sp3 and here are 2 sp3s that are linked together, but they're pretty darn similar. In the case of where we have sp2 hybrid orbitals, where we have a double bond, the core of the atom or of the molecule looks pretty similar. You can compare that here, here, and here. So once you get the gist of how to draw these and how to interpret what's going on, there aren't that many combinations. Okay, let's look at question 7. Consider the amino acid phenylalanine. How many sigma bonds and pi bonds are in the molecule? Let's start with that first part. So one of the things we know is that every time we have a single bond, we have a sigma bond. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I knew I missed one. 19. And every time we have a double bond, it's a combination of a sigma bond and a pi bond. So that must mean I've got some more sigma bonds. 1, 2, 3, 4. So that means 23 sigma bonds. But let's go back to our double bonds because the double bonds have pi bonds in there. The second bond is a pi bond, pi bond, pi bond, pi bond. So that means I've got 4 pi bonds. 23 sigma bonds, 4 pi bonds. Now, the second part of the question is for how much of the molecule can you draw a valence bond theory picture? I'm not actually going to do this in this video, but you have all the pieces that you need to do it. So for example, this carbon, as a central atom, has 3 regions of electron density around it. That is going to mean it's trigonal planar. It's going to look like an sp2 center. So it's going to look something like this. This carbon is tetrahedral. So it's going to have 4 regions around it. It's going to be sp3 and it's going to be tetrahedral, kind of like this carbon here. So I wouldn't expect you to be able to draw the whole thing all connected together, but I would expect you to be able to pick out some pieces and draw what they look like. All right, this next one is kind of a fun question. I think it's fun. Are the hydrogens in the following molecule all in the same plane? Draw a valence bond theory picture and explain your reasoning. So first of all, we have to draw the Lewis structure. So let's stop and do that. So here's the Lewis structure. And the question is really asking, are all of these hydrogens in the same plane, which is kind of what it looks like. I've drawn it as though it's a flat molecule. Or are they not all in the same plane? And can we use valence bond theory to help us predict what that would look like? So let's start at one end of the molecule. Here's a carbon. It's got 3 regions of electron density around it. So that must mean that carbon is going to use sp2 hybrid orbitals. So we would draw it like this. Here's a carbon. Here's an sp2, sp2, and sp2. And I've drawn these sp2s. So this one's coming out of the plane of the paper. This one's going back. So it's perpendicular to the plane of the paper. I can draw my hydrogens. One's behind the plane of the paper, one's in front of the plane of the paper. If I go to my second carbon, the second carbon has 2 regions of electron density around it, so it's going to be sp hybridized, and I'm just going to draw those hybrid orbitals in a different color. So this is an sp and this is an sp. If I go to my third carbon, it's got 3 regions of electron density around it. And actually, let's not draw it yet. Let's just keep going with these first 2. So we've accounted for one of the 2 bonds. Notice I've got a sigma bond going here. And I've got a sigma bond with a hydrogen, sigma bond with a hydrogen. But these 2 carbons have to have another bond. They have to have a pi bond. So let's draw the p orbitals. These particular p orbitals are in the plane of the paper, and we've now formed a pi bond. The central carbon has another p orbital that comes out of the plane of the paper and goes behind the plane of the paper. And how do I know that? Well, these 2 p orbitals here, they have to be perpendicular to one another because that's what p orbitals do. So now let's go to that third carbon. So this carbon, 3 regions of electron density, it's also going to be sp2 hybridized. And it's going to have a p orbital, and we're going to need that p orbital, we're going to need that p orbital to be lined up so that it can overlap with the p orbital on that we haven't used yet. So if that's true, then when I draw my sp2s, they are going to have to be in the plane of the paper because the p orbital has to be perpendicular. This p orbital has to be perpendicular to the hybrid orbitals. And so if I just add my hydrogens in now, notice that I've accounted for all the bonds, sigma, 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 and I've got 2 pi bonds, one that's here and then one that's coming out here. Let's go back to the question we're trying to answer. Are the hydrogens all in the same plane? The answer is no. This one's coming out of the paper, this one's going behind, so they are in a plane that's perpendicular to the page, and these are in the page. So they are not all in the same plane. Now, if it's difficult to see that, and I think it is when you're first learning to visualize it, I encourage you to go into the CIC and have someone show you with a model kit what this molecule would look like, and it will make a lot more sense.